You might have noticed that circular motion can be described in a very similar way to one-dimensional linear motion. For example, angular velocity, the speed at which an object travels around a circular path, is defined as the angular displacement divided by the time interval, exactly analogous to linear motion. It turns out that we can define a quantity that is analogous to a force, but in a rotational context. There's a little more involved than simply assigning a value for F, but I think you'll find it's actually quite intuitive. Take a simple case of opening a door. In order to rotate the door, we need to apply a force. However, where we apply the force matters. Given the choice of where to push, you would likely say that you get the best results when you push at the end of the door that is opposite to the hinge or the pivot point. So if we think of a force as something which can make a stationary object start to move, the rotational analog of force will depend both on the applied force and the distance from the pivot point. We can define a quantity called torque as the product R times F. Since the rotation can be either clockwise or counterclockwise, we will define a torque to be positive if it attempts to rotate an object in the counterclockwise direction. Now, before we even address the resulting motion, it's worth taking a look at situations where multiple torques might be acting on an object which overall remains at rest. Suppose you're holding up one end of a plank with a weight sitting on top. The two forces acting on the plank want to cause rotation in opposite directions, but since the plank is motionless, the net torque must be zero. We can imagine a pivot point at the right end and use this to calculate the two torques. The magnitude of these torques must be equal, which means that we can say something about the two forces based on what we know about the distances. Since your force is 3 times further from the pivot point, you must only have to apply 1/3 of the force in order to generate the same torque. Now, here's a final important point. We don't have to assume that the pivot point is on the far right. What's important is that when an object is not rotating, then the net torque must be zero, regardless of where the pivot point is located. Use this idea to compare the normal force to your applied force if you assume that the pivot point is located at the position of the cow.